Welcome to the Coursera class on galaxies and cosmology. My name is George Jorgovsky, and I'm a professor at California Institute of Technology. This class is offered to the second-year physics and astronomy students at Caltech. Therefore, it requires a certain amount of preparation, and we'll come to that in a moment. But first of all, let us define what is cosmology. It is the science of the universe as a whole and its major constituents, how they work and how they evolve, how they form. It is different from cosmetology, and if you made that mistake, this would be a really good time to stop. Well, it's not an easy task. The universe is very big, and we cannot reach it all. We can just sit here and watch. And so we have to make some assumptions. The basic assumption that we make is that laws of physics are same everywhere and at all times. This is a very reasonable assumption, and if it weren't true, it would be very hard to do any kind of science. But we can actually test some aspects of this proposition. Moreover, sometimes, while studying the universe, we discover things in physics that we didn't know about. Notable examples are nature and existence of dark matter and dark energy, and we'll talk about them later in the class. Unlike most other sciences, cosmology has only one object to study. There is only one universe in which we live. And all we can do is sit and watch, or in technical terms, we can look at the surface of the past light cone. So there are parts of the universe that are a priori not observable to us. We're pretty much sure that they do exist, and they're probably not very different from the parts that we do see, but it's something to keep in mind. And also, things are far away, and therefore they're faint and small, and we need most advanced technology to do this. This is why cosmology really flourished as a science in the latter part of the 20th century, because before then, we simply did not have good enough tools to do it right. But even so, we have to be always aware of possible biases and selection effects. For example, there could be some very faint galaxies that we're missing. Cosmology responds to the basic human need to understand the big picture. Where is it all coming from? How does it work? Where is it going? And it evolved through time. In the pre-scientific days, creation myths were made to answer these questions, but they really were just made-up stories. Then starting from beginnings of modern science in the Renaissance and the Enlightenment, things started to get a little more rigorous. First, the Copernican revolution, which was a major shift in the way people think about the universe or the world, that posited that we're not at a special place. The Earth is not the center of the universe, it's just a random spot. Cosmology actually uses this in a so-called cosmological principle that we'll define in a bit. But not only that, the universe is not static and unchanging. We see it change. And just like biology and planet Earth, the universe evolves on its own. And following laws of physics, major constituents of the universe, galaxies, stars in them, also evolve. And we can understand how that works. And just like anything else in science, it became subject of study, and therefore it is always improvable. We are not declaring anything with absolute certainty, but we're actually trying to understand what's going on. And like in other science, the more we push further, the more we learn, the more new questions we open up. And that's the nature of science, and this is very good. So, whereas really cosmology started as a branch of astronomy as a whole, certainly cosmology became a branch of physics, because we use laws of physics and principles of physics to obtain our measurements, to understand them, to interpret them, make predictions. All right, now let us find out how well prepared you are for this class. First, we'll do a few quizzes. Let us now resume our journey to the universe and dust off some of the astronomical units of measurement. The most basic unit in astronomy and cosmology is distance from the sun to the Earth. It's 1 astronomical unit, and it's about 150 million kilometers. There is, of course, the light year, which is the distance that light travels over 1 year. And 1 light year is approximately 10 to the 18th centimeters. Now, astronomers almost never use light years. We use parsecs, which is the distance from which 1 astronomical unit is seen at an angle of 1 arcsecond. And that turns out to be roughly 200,000 astronomical units, or 3 times 10 to the 18 centimeters. So when we talk about parsecs, or kiloparsecs, and megaparsecs, and gigaparsecs, you can multiply that by 3.26 to get corresponding number in light years. 2 basic properties of objects that we need to understand are masses and luminosities. And for convenience and historical reasons, we use solar mass as a unit, and that is approximately 2 times 10 to the 33 grams, and solar luminosity, which is close to 4 times 10 to the 33 ergs per second. So you can convert them to other units as you need to. You should really remember these numbers, because we'll constantly refer to distances and masses and luminosities using these units. Now, what we observe are fluxes. We mostly observe electromagnetic radiation, although we now have forms of astronomy that are not dependent on electromagnetic radiation, like cosmic rays, neutrinos, and soon enough, gravitational waves. But flux is what's measured, and we have detectors that can operate in full range of wavelengths from radio to gamma rays, and they're usually measured over some finite bandpass. So spectral energy distribution, which is the shape that describes the spectrum of an object, is defined to be energy per unit time, per unit second, per unit for frequency or wavelength. And we never observe that. That's a differential unit. Instead of that, it's always observed over some finite bandpass, like an optical filter or bandwidth in radio astronomy. One unit that is often used is Jansky, which was introduced by radio astronomers, and it's 10 to the minus 23 ergs per second per squared per hertz. Optical and infrared astronomers are now beginning to use Janskys as well, although we're typically talking about micro Janskys and nano Janskys. So this is often called flux density, and to get really the power of object, one has to integrate it over all bandwidth and then multiply by the area that's collected. Astronomers use magnitudes, which are a logarithmic measure of flux, defined by the formula written here. A magnitude is minus 4 decibels. The minus sign tells you that the higher the number means the lower the flux. And because it's a log, it's a relative measure of flux, relative to some unit flux. In log, that comes as an additive constant. Typically, flux is measured over some finite bandpass, like V-band filter centered on 5,500 angstroms, and then log of that times minus 2.5 plus a constant 0 point that I'll define in a second gives you the actual magnitude. If for some reasons you could integrate the flux over the entire spectrum, then this will be called the bolometric magnitude. Now, magnitude 0 points are another part of astronomical craziness that's unfortunately well established and hard to change. For historical reasons, again, Vega, which is Alpha Lyrae, was declared to have 0th magnitude, and then everything is measured relative to it. Notice that because we're talking about logarithms of fluxes, we're talking about ratios of fluxes, and so it's all relative to some unit. Well, that unit for magnitude systems is usually Vega. And unfortunately, its spectrum is not flat. It looks like this. There is also a more rational kind of magnitudes that's been introduced. It's called AB new magnitudes, which are with the fixed 0 point, as the formula on the bottom shows. But typically, people use Vega-based magnitudes. And it's a handy way to remember it that 0th magnitude star corresponds to almost 1,000 photons per square centimeter per second per angstrom. and you can scale from there. Now, magnitudes are measured. It's apparent magnitude. What we like to do is know how luminous an object really is, and therefore we need to know how far it is. So an absolute magnitude was introduced, which is the apparent magnitude object would have if you observe it from a distance of 10 parsecs. Why 10 and not 1 is anybody's guess, but this is the definition. And so if you put sun, or sun-like star, 10 parsecs away from us, it will have apparent magnitude of roughly +5, different in different bands because the spectrum shape is different from that one of Vega. So as a handy measure of the distance, sometimes we use the difference of apparent and absolute magnitude, which is called the distance modulus, and it's equal to 5 times log of the distance divided by the 10 parsecs. So this is how you can convert this. All right, so this is it for now, and the next time we'll start talking about history of cosmology from the earlier days to the present time.